In this video, we present a proof of twin prime conjecture using twin prime model table and Sieve functions. Twin prime conjecture states that there are infinitely many prime numbers with a distance 2, like 3, 5, 11, 13, 17, 19. It is unsolved since Polyak generalized the prime gap to K in 1849. Our ideas are: we introduced twin prime model table to show rules for finding twin primes, and introduced Sieve functions to functionally represent rules in TPMT. Let's consider where can a twin prime pair be found in odd number sequence. If a multiple of 3 exists between two odd numbers, the difference between two possible prime numbers will be 4, failing to be a TPP. For example, 9 is a multiple of 3, so the gap between 7 and 11 becomes 4. So removing multiples of 3, possible TPPs must have the form 6n minus 1, 6n plus 1. You can see examples here, and we use the notations down and up. This is down number and this is up number. Let's see in more detail about the TPMT. First, we see the horizontal arrangement. N is the sequence of the rows, and this is down number, and this is up number, and down number, up number pairs are all arranged horizontally. And seed means a number in the first row, like 5, 7, 11, and it is used in sieving vertical 6n minus 1, 6n plus 1 pairs, which means these pair blocks are sieved by these horizontal numbers. The vertical arrangement consists of these 3 combinations: sequence, down number, and up number. And primes are marked as red. The red numbers are primes, and TPPs marked as red n. If n is red, is a twin prime. Let's see about the inner cells. You can see 1D, one new pair appears diagonally, and it means this pair is always divisible by itself. 5 divides down number 5, and the quotient is 1. 7 divides up number 7 itself, and quotient is 1. Here 5u means 5 divides up number 25 with quotient 5, and here 5d means 7 divides down number 35 with quotient 5. If this kind of value appears as a cell, this cannot be a twin prime pair. But like this one, if all cells are empty except this 1D 1U pair, it is a twin prime pair. So we hope you understand the rules of finding TPPs in TPMT. We present an example table here, and you may have some time to look into in more detail. Let's define phases. Phase is value of n where the first downward MD or MU appears. There are two kinds of phases, down phase PD or phase PU. For example, for seed 7, 1U appears at n equal 1, so up phase is 1, and 5D appears at 6, so down phase is 6. For 11, 1D appears at 2, so down phase is 2 and up phase is 9. This table shows the phase patterns. So TPP can be interpreted as Sieve view. Here C's are horizontally arranged and N is also horizontally arranged. So sieving these pairs is transformed to sieving number sequence n. An arrow means sieving a number from this number sequence. Unsieved n is a TPP, like 5 here. Sieve view of TP is if seed values can sieve all integers after some specific number omega appears here. It means that TPPs are finite and so TP is false. Let's define Sieve functions. We showed two Sieve functions here. It is a sine function and Pi is primes. Multiples of Pi are zeros of Fi. We can say that numbers are sieved by Fi, but when t equal 1, it is considered unsieved, like 2 or 3. Let's define phased sieve function. Phased sieve function is product of two sine functions, di and ui, where di represent down sieve function and ui represent up sieve function. Si is the ith seed of seed sequence, yes, and PDPU is phase pair of I seed. We showed seed for 5 and 7, and you can verify the down phase, up phase, and period, up phase, down phase, and period. Here we defined composite phased sieve function. It is product of PSFs like this, and we showed an example graph here with the period Q is the multiplication of two periods of H. We can functionally represent TPMT sieve rules. This example is for seed 5. The sequence n is sieved by di and ui, and down phase is used here, and up phase is used here, and the red graph sieve out natural numbers on x-axis, which is same as sequence n. So these three sieve functions represent the sieve rules in TPMT. For seed 7, the situation is same as before. Sequence n is sieved by di and ui. Up phase is used here. Down phase is used here. And rules in TPMT is implemented as these three sieve functions. Here we sum up our ideas. You know Euclid's theorem that there are infinitely many prime numbers, and to prove it, multiply finite number of primes and add 1 and prove Q is a new prime. Sieve function view of Euclid's theorem, we can say any composite sieve function can sieve all integers after some specific number omega. We show two graphs here. If functions cannot erase or sieve out all integers after some specific number omega, primes can't be finite. The second gist is only sieve functions with period 1 can sieve all integers after some specific number omega. This function type can be like this or like this, and we show the two function graphs here. Here we showed CPSF again with these properties, and graphs are given here. The gist is any multiplications of sieve functions with a different period greater than or equal to 2 can't sieve all integers after some specific number omega. Only px can do that. Hk cannot be equivalent to px. It's because the orthogonality of sieve functions. In a sense, SF cannot be replaced by any combination of other SFs. The last gist is about the generalized prime gap 2K, and can it be proved by our logic? Now we have two lemmas, and first lemma states that H is periodic with period Q. It is so obvious. And second lemma is H can't make all integers after some specific number omega as sieved n. As we said before, H is finite period function with a non-sieved n within its period. So it will repeat infinitely many times its period, which means that it is impossible to make all integers after a specific number omega as sieved n. Lemma 2 can be the proof of TPC. But we suggest lemma 3 as the proving lemma. There are infinitely many TPPs. Let's prove by induction. Step 1. At k equal 1, there are infinitely many unsieved n of the sieve function h1. Step 2. Suppose at k, there are infinitely many unsieved n of the sieve function hk. Step 3. Then at k plus 1, adding a new seed as k plus 1 cannot change that hk plus 1 is a finite period function with unsieved n within its period. So, by lemma 2, there are infinitely many unsieved n of the sieve function hk plus 1, leaving infinitely many TPPs. Thank you.